All right, let's do some mechanics. So first, we're going to start just by going through some questions that I'm sure you're probably thinking. So first, unfortunately, it's only Form J that's released right now. There might be plans from College Board to release other forms in June. There's an AP Classroom post about it that maybe more forms will get posted once testing week is done. So maybe they'll release that West Coast Form L would probably be the other one. And maybe Form K gets released to AP Classroom at some point. But for now, we just have J. So all of the forms have different cuts. So if we look at Form J and you're like, this is easy compared to mine. Well, your cut is probably lower what you need on the harder form. Now, on that topic, yes, it was absolutely true that last year on mechanics, to get a 5, the cut score was 78%. The teachers have data to prove it. It was a very organized, methodical technique to determine the cut, but that's last year. This is 2026, not 2025. And these questions are a lot more involved, or at least 2 of them are much more involved than last year. If you look at last year's mechanics questions, they're pretty straightforward, except for maybe the 4th one. So there's some more intricate topics going on with this year. So what will the cut be? Who knows, right? I mean, you took the test already, so not much we can do about that. We just got to wait till July, and we'll reverse engineer it like we always do and see what the score changed to. But with that, I think we will start. So this was one of the harder questions that I've seen in quite a few years, honestly. This was probably something quite scary to open your booklet to see this. So we have a cube inside of a box, and the box cube system is moving to the right. There's no slipping happening, and there's this sort of drag force. There's this drag force that's acting on the box, and it says from t equals 0 to t crit, the system is slowing down, but the cube remains sort of stuck to the side of this box. And then at t crit, the cube begins to slide. So initially, everything's all stuck together. It's one system, but eventually it's not. And we're going to be asked some things. So first, it says the normal force is Fn. We want the acceleration of the cube. We're only allowed to use m and normal force. All right, well, if we want acceleration or net force or anything like that, we probably want to draw a free body diagram. So got my lovely asymmetric box here, and then I have my cube that's inside the box. And then we can think about the forces that are acting on this cube that are inside the box. So, of course, this cube, mg, straight down, right? Now, what is preventing the cube from falling? Well, it's stuck to a wall, so there must be some force preventing that sliding down the wall. So that is, of course, a static friction force. And we actually know these forces have to be equal because it says the box is at constant height, or the cube is at constant height, rather. And the cube is touching a surface, so there will be a normal force exerted on the cube by the wall, which is causing the cube to slow down. So this is a lot easier than it looks. We just want the acceleration. So we know that the acceleration, according to Newton's second law, is just the net force on the object divided by the mass of the object. So we're just looking at the cube specifically. So the only thing, net force is help minus hurt, right? So there's nothing helping the cube move, but the thing that's opposing its motion would be the normal force. So the net force would be a normal force, and the mass of the cube is just one singular m, because those are the only forces acting on this singular mass m. Now, of course, if you did it negative or something, that's fine. We just want the magnitude. So it really would be a Fn over m that's going to be slowing down the cube. So this is probably worth 2 points. You get a point for Newton's second law, I imagine, and then you get another point for the correct answer. Now here's where it ramps up. Derive an expression for normal force while the cube is in this position. So now we've kind of done everything we can with the cube, right? Because the only things that are this is a full force analysis of the cube. So now we got to zoom out to the entire system. So now what we have is essentially we're going to just wrap this entire thing in a box. So whenever there's a force outside your system, a good technique is to just collapse the whole thing into a single system if everything's accelerating together. So I can just model the entire system as a 2m mass, and there's only one unbalanced external force acting on this system, and that would be this sort of resistive drag type force. BV. So my net force on the entire system is just going to be the drag force, and there's nothing helping the motion of the system, so I'm just going to make the drag force negative. So our equation would say that our system has mass 2m times its acceleration would be negative bv. So this means the acceleration of the system would be negative b over 2m times v. Well, this doesn't help us get normal force. So it seems like we have to get acceleration, because this acceleration is going to determine the normal force, because Fn over m is acceleration. So if we can determine this acceleration in terms of the quantities, we can just plug into our previous expression to get normal force. So this is actually a differential equation, because we just found that acceleration, which is the derivative of velocity with respect to time, is equal to negative b over 2m times the velocity itself. So we solve this like any other separable dE, where we separate our v's and t's. This is a pretty classic differential equation setup. Nothing too wacky here. The scenario's weird, but this is pretty standard, where we start at some velocity VO and end at some velocity V later, and we go from 0 to t as per usual there. dV over V, that would be natural log. So natural log of a difference becomes a quotient, right? ln V minus ln V0 can be collapsed like that, and the other side integrates just to t. So now to simplify, we can exponentiate both sides. Because if e and ln touch, they cancel. So we get V over V0 is equal to negative e to the negative b over 2m times t. So V is V0 e to the negative b over 2m times t. And this should make sense. This is a pretty standard velocity-dependent force equation that you get. Okay, so what does that mean? Well, that gave us V. So now we can just plug back in. Now I can just plug back in for our acceleration, because we just said acceleration is equal to negative b over 2m times v. So we can take this equation here and plug that back in there for v. So this means a would be negative b over 2m times v0 e to the negative b over 2m times t. And then to find normal force is just that times the mass. So it said the normal force is just going to be ma, according to this expression, because the normal force is the net force on the cube. So all that does is that just takes out the m from the denominator. So I get negative bv0 over 2 times e to the negative b over 2m times t. And I'm sure that's exactly what we thought the normal force would be as soon as we saw this problem, right? I'm sure we knew it was totally going to be this decaying exponential. Yeah, that's hard. Oh, okay. Only 3 points out of this, though. I got to figure out how to get 3 points. Now, of course, this is the 5th point for this. Now I got to get 2 more. So I imagine one of the points will be some sort of net force equation equivalent to this one. Finding the acceleration of the system, I imagine, is probably getting you your first point, is relating the drag force to the acceleration of the system. And I'm almost certain that there will be a point for just finding v of t. And then probably a consistent substitution gets you a5. I don't know if it has to be correct or not. That's kind of for them to determine. Sometimes the rubrics may get correct. Sometimes it's just consistent substitution. It kind of varies. So only 3 points out of that, but that took a lot of time. All right, now for our final 2 points in A, we have to make a graph. So sketch a graph before the friction for the friction force on the cube at these times. So what is T crit? Well, T crit is the time where the block begins to actually slide down. So it might help to like describe this, where this is at constant height. So this is where the block is frozen to the surface. It's frozen to the wall. And here is where the block is sliding down the wall. So we know at constant height, if there's constant height, the forces must balance. Now, if I look at my free body up here, we see that the static friction force is exactly balancing the weight of the block. So it is just mg all the way. So before it starts to slide down the wall, we just have that. Is it really not going to let me draw a straight line? There we go. Straight enough, I guess. Technically, this value is mg. We know what it is, so we could actually label it if we wanted to. And then what happens after we begin to slide? So it's important to note that the static friction force, it just has to be mg. So there will be a point where the static friction force can't supply the mg you need because of that decreasing normal force, but it's constantly at mg because the downward force doesn't change at all. But there will become a point where the normal force is too small to support this scenario, which gets us to sliding down the wall. So first of all, we said before T crit, the force of friction is just equal to the static friction force, which is equal to mg. But then after T crit, it slides. So when you get sliding, that's kinetic friction, and kinetic friction is always equal to mu k times the normal force. And from the previous part, we said that the normal force is this decaying exponential. So we got this decaying exponential function. So this is a decaying exponential. So I should also get a decaying exponential for my frictional force. And I'm not sure how they're really going to grade this, but we also need to remember that kinetic friction is less. So at this transition point, it's actually a jump discontinuity due to that fact that kinetic friction is always, the coefficient is less than for static friction. So we have to know that. Now, I have no idea how they'll actually grade this. Like, this is certainly a point. A6 being a constant flat line is probably a point. And then I don't know if you need to get the jump or just the decay. It depends. That's a tricky graph. I had to think about this for a little bit. Do you think we get easier? No. Drive an expression for T crit in terms of lots of things allowed now, including mu static. This should really have clued you in on what's happening here. The fact that mu static is allowed in the answer. So there's only one equation with mu static in it. And that says that the max value of static friction is mu s times the normal force. So when we saw that mu s is allowed in your answer, this is the only equation that has mu s in it. So what we must be doing, which makes sense, is looking at the maximum value of static friction. Because at T crit, we're finally beginning to slide down the wall. So that means that static friction is finally defeated by mg, because this normal force is too small to support the necessary friction to counter the weight. So we can just set Fs max equal to mg. So mu s times the normal force is equal to mg. And we found the normal force earlier. The normal force was this absolutely beautiful expression, bv0 over 2 e to the negative b over 2m times t. I sure hope I didn't mess that up. I think I should double check just to be sure. I have this negative. It doesn't matter. I might change this just to... It doesn't matter if it's negative or not. I'm not going to make it negative because I wanted the magnitude, but I was just making sure I copied my force right. All right, and now it's just an algebra problem. So this is really a pre-calc problem at this point, not really an easy one. There's a lot of symbol moving around. I actually think it's going to be easy to get points on this B part because the weeds of the algebra is probably just 1. All right. So I can get e to the negative b over 2m times t is equal to, move the 2 to the top and move mu s, b, and v0 to the bottom. Now I want to get what's in this exponent. So I have to take the natural log of both sides because if ln and e touch each other, they cancel. So I get negative b over 2m times t is equal to the natural log of this lovely item. And then we can solve. So t is just going to be negative 2m over b, natural log of 2mg divided by mu s times b times v0. And this should look kind of wrong. This should definitely look wrong because I just got a negative time, it looks like. Well, actually, this means the logarithm term is negative. You get this a lot with like half-life stuff because if this fraction is less than 1, the logarithm term is negative. So if that bothered you, you could have also written this as you can get rid of the negative sign and flip the fraction upside down. Some people find that better to look at because they don't like this idea of a negative time. So this is acceptable, and this is also acceptable. So how you get points here, almost certainly B1 is probably this for saying that it's static friction's max value. You probably also get a point for substituting in your normal force to this equation. So if you substitute into this equation, that's B2. And then B3 is the correct answer. Good luck with that. I cannot, I have no idea what the nation average is going to be for this question. I don't think it'll be particularly high because even the graph points are tricky. Yeah, that's one of the harder ones I've seen in a while. Yeah, that took me almost 20 minutes. And it takes me usually no time to get through these FRQs. All right, now we have number 2. This is actually one of my favorite questions I've done in a while. I thought this was neat for a lot of different reasons. So here we have a block of mass 4m. It's launched as a projectile, and then it explodes at the top of its trajectory. And one of the pieces, 1/4 of the mass, flies backwards, so it lands where it started. And then the other piece lands at some distance x2 that we want to calculate. So anytime you see a kaboom, it's probably momentum. So this is a mix of projectiles, kinematics, and momentum. I've asked a variant of this actually on my practice exam 1 or 2 maybe. So if you've done that one, you've actually seen this question recently. I did the fall straight down version of this after the boom. So now we got bar charts. So we have the momentum of the projectile system when we first launch it, and we want to figure out the momenta in each dimension of all the pieces right when the boom happens. So that's right when the split happens at the top of the trajectory. So what we know is that anytime you have a projectile, there is no net force in the x direction because gravity is only acting in the y. So there will be momentum changes in the y direction, right, because you're accelerating. But in the x direction, there is no net force on the system. So this means the momentum in the x direction must remain constant. So we know whatever we do, we have to make sure the x momentum stays constant. Now, we can see there were some strategically plotted bars here because our x momentum would be 1, 2, 3, 4 momentum units. So I'm going to call this like 4 mvx. And this looks like 2 vertical momentum units, so 2 mvy. Now, what happens after the explosion happens? Well, after the explosion happens, notice that the small piece lands where it started. So by symmetry, the small piece must have been shot backwards with exactly the same speed it had forwards initially. So this must mean that the velocity of the Q piece is exactly the opposite of the speed in the x direction that it was launched with. So if the entire projectile moved backwards at the speed it started with, I would have 4 bars of negative momentum. But it's not the whole projectile. It's only a fourth of the projectile that's moving backwards at that speed. So I'm going to give that exactly 1 bar of negative momentum. So negative mv0. And then in the y direction, well, we're actually at the peak. So if you're at the peak of your trajectory, there's no speed because that's when you're going from traveling up to traveling down. So this is that turning point. So 0 momentum there. So for a similar argument, there's 0 momentum in the y direction for piece r. And then to figure out r's final momentum in the x direction, we just got to conserve because we said total momentum remains constant. So if I originally had 4 bars in the x direction, I must end with 4 total bars in the x direction. So I have negative 1 bars given to the q piece, so I must have 1, 2, 3, 4, 5 pieces given to the x piece. So notice my sum remains constant in the x direction, not the y, and that's totally okay, because gravity is an external force on this system, so there's no reason the momentum should stay constant in that direction. So how would I grade this? Well, I think the easiest point is, out of the 3, this is part A actually, I think the easiest point out of the 3 is to say the y momentum is 0 for both pieces. Now to get A2, you would probably have to say that P of the momentum of Q in the x direction is negative 1 unit. So you'd have to realize it's negative 1 unit on this chart. And then to not double ding you, A3 is probably the sum of your x momentum has to be positive 4. So just showing that momentum is conserved should get you A3. So if your x bar is added up to 4, regardless of what your q bar was, it should work out. I imagine this is how they score it. Now the derivation, this is where the fun begins. Find the range of the big piece. So what is happening here? So we should really think about this as like 2 phases. So first, we have the entire system, which is going to move some distance before it reaches the top. We'll call this like 0 to t1. So first, the whole projectile is going to fly up. It's going to reach the top of its trajectory, and then it's going to go kaboom. Now, what happens after that is we know that there's eventually going to be some piece moving backwards. But this also means that our 3 piece is going to be moving forwards at a higher speed than before. Because if this piece gets blasted backwards, we have to have a faster speed this way to make the momentum stay constant in that direction. So we're going to have a bigger speed there. So these are not the same distance. So we're going to find the distance of these in 2 phases. Now there's also a nice center of mass approach that you could also take with this, where you say the speed of the center of mass in the x direction stays constant, and then you do this sort of average positioning thing. I don't know if that's the most straightforward way. I did it to check my answer originally, and it works, but I think this way is probably the most straightforward and is probably the intended one. So x2, the range, is going to be delta x when everybody is together, plus the delta x of the big piece while it's falling with its new velocity. And since there's no acceleration in the x direction, we can say that the range is going to be the x velocity of the projectile system at the start times the time it takes to get to the top, plus, I'm going to call this VR for the speed of r because it changes. It's not the same speed, also times t top. So we know that the time up is going to be the same as the t down. So this is going to take some time t to the top. And this is also going to take some time t to the top because nothing interesting is happening vertically. So it's nice and symmetric. So there's quite a few steps that need to happen here. So we have two things to determine. We have to determine t to the top, and we have to determine v of piece r after the explosion. And then we can just plug and chug. So for t top, I would just use kinematics because we know that at top, Vy is equal to 0. So I can just use the kinematics. Vy equals Vy0 plus At. So 0 is equal to Vy0 minus G times T. So T to the top is just going to be Vy0 over G. And we're going to do some like trig substitutions for the X and Y components. I'll just do that at the end. Because it is just going to be like our basic, it's just going to be our basic projectile where we have V cos and V sine as our velocity components. So we'll substitute those in at the end. So also at the top, we have to do momentum conservation. So we also know that Px at the start, or Px is equal to a constant. We'll just say that. I don't want to deal with a million subscripts. So since the momentum is constant in the x direction, well, originally we have 4 blocks all moving at velocity vx. Then afterwards, we have 1 of the 4 blocks moving backwards at vx, and we have 3 of the blocks moving at whatever speed r has. So we can work this out, and we would see that if I add this to both sides, I would get 5 mvx, so vr would be 5/3 of vx. Also, there's like lots of substitutions you can do here if you just see some different insights, and I think I'll talk about those at the end. All right, so now we just plug and chug. So this means that x2 is going to be vx times t top plus vr times t top, which we said was 5/3 vx times t to the top. So that's going to be equal to 3/3 plus 5/3, which is 8/3 vx t to the top, which gives us 8/3 times v cosine theta times v sine theta divided by g. And this looks very similar to the range formula, which makes sense because it is a range. So I'd get 8/3 v0 squared sine theta cosine theta over g, or 4/3 v squared sine 2 theta over g if you use the double angle identity. Wow. Now there's some like quick approaches that could get full points on this as well. One of them would be finding the range of like the center of mass and then doing like an averaging thing. But I don't really know if that's the most efficient approach for most people. I think this is probably one of the better ways of doing it. So if you want to do the center of mass, I'm sure somebody will outline it in the comments. I did it on my other copy of this just to check my answer, and it of course agrees. So how do you get points here? Well, I think you get a point for something about like, well, I think you get a point for something about saying this fact that like it's 2 ranges being added together maybe. Then you probably get a point for figuring out t to the top. Then you get a point for figuring out v of the other piece using momentum, and then b4 is the answer. Now, if you did center of mass, I'm not totally sure how that would distribute, but I imagine it's a similar distribution because you still need t top for center of mass, and you still probably need some form of momentum conservation. It's just written differently. Yeah, the time is really ticking here. This is way longer than this ever takes. These are some involved questions this year. All right, we have plotted the x velocity of the center of mass before the explosion, we want to plot the x velocity of each of the pieces and the center of mass. Well, first, no external forces in the x direction, so xcm stays constant. Then we said that for the Q piece to land where it started, it just got launched backwards at its original speed. So the Q piece is just backwards. But for the Q piece to fly backwards at that velocity, the R piece must have gotten shot forwards and was given a little boost. So the R piece was given a little boost. We actually figured out it was 4/3. We actually figured out it was 4/3, or sorry, 5/3 of the center of mass x speed there. So yeah, this is an interesting problem. And then we're not done yet because we actually have a like how does it change question. Consider a case where instead of blowing up and Q going launched backwards, we blow up and Q just falls straight down. So I have two ways that I was able to think about this. So if we look at our picture, if we're at the top and we explode and send a piece backwards, well, what that does is that means that I have given some negative momentum bars to the Q piece. So anytime I'm giving more negative bars to this one, I have to give more positive bars to this to make the sum the same. So if instead I just drop the piece straight down, your momentum is smaller in the negative direction, so your momentum is smaller in the positive direction to compensate. So the speed is lower and the other piece doesn't fly as far. So another way of thinking about this is that the speed or the momentum of the Q piece is going to change less if it goes from, it's going to change by less if it just drops straight down. And since any change to the Q piece must also be reflected oppositely in the R piece, well, if there's a lower momentum change for Q, there's a lower momentum change for R, so R doesn't speed up as much, so it is slower, so it doesn't land as far. So that is this approach. If piece Q falls straight down, Q has a lower momentum change than before. Since momentum change is equal and opposite, for conservation to hold, R also has to have a lower change. Thus, speed R speeds up by a lower amount and doesn't go as far. Now, for center of mass enjoyers, I said this. The position of the center of mass will actually be the same in both scenarios because you start with the same center of mass velocity. So the center of mass of the two piece system can't change. And as a result, if Q falls straight down, that means that Q is going to be more to the right than it was before. So in order to keep the center of mass from shifting, if Q moves right, R must move left so that they average to the same spot. Weighted average, of course. So I like both of these. So we had to say that the new range is lower. So that's how you get D2 or D1, is you had to say the new range is lower and some sort of justification. So I think equal and opposite momentum changes is probably the point there, and something about center of mass staying constant between the scenarios is one. So I'm actually working kind of at the suggested pace, which is a reflection that this is hard, but this was really front loaded because the last two questions are nothing, especially not the last one. Lab question time. Oh, whatever are we going to do? What could this be about? It's a spring and friction. Who knows? Okay, spring is attached to a wall. We put a block on it. We want friction coefficient mu k. We are only allowed to use a meter stick. And we have to graph two things. So if we have a meter stick only, that must mean the meter stick must be getting two unique things. So we have a block. It is placed against the spring but not attached, so I can compress the block against the spring, let go, the block will get launched. So what's going to happen is the block is going to get launched and it's going to get stopped along this rough surface. So we have two things to measure. Here's how you get all your A points. We can just say measure blank, measure blank, repeat for multiple values of blank. All right. Well, what are we measuring? Well, it's definitely distance. So what distances are relevant? Well, if it's springs, the relevant distance for a spring is going to be the compression or displacement delta x. And if friction is stopping you, this is definitely like a work problem. So we're going to be interested in the distance d it takes for the block to stop. So we're going to measure the spring compression, which we're going to call delta x, and we're going to measure the stopping distance, which we're going to call d, and repeat for multiple values of delta x. So I get A1 for both of these measurements, and I get the garbage uncertainty point for just saying repeat for multiple values of compression. So how can we graph this? Well, this is energy related. So anytime there's no time, it is usually energy related. If you don't know anything about time, it's probably some sort of conservation of energy. So what's happening? Well, energy stored by the spring is being dissipated by the frictional force. So the energy stored in the spring is just 1/2 k delta x squared. And then the work done by friction is, well, we know that work is going to be the force value times the distance the force acts over, because everything is nice and horizontal. And this is kinetic friction. So kinetic friction is always mu k times normal force. It is fixed. And we're on a flat surface, so normal force is just mg. So I can say 1/2 kx squared equals mu k mgd. Now we can check that we know these things. So it says that the known constant k is associated with the spring, so we know k. We know the mass m, and the only thing we're missing is the coefficient of friction. So let's go through our list. So we measured delta x, that's a variable. We measured the distance d, that's a variable. We have m, we have g, and we have k. So that totally tells me this is a setup that we can do. So now all we have to do is figure out what to graph. So I just pick one of the sides to solve for. So I'll solve for just leaving one of my variables. I'll just leave x squared on the left side. That's less amount of symbols to move around. So I can get delta x squared is equal to, I'm going to put everything in front of the variable. So I have to multiply by 2, and I have to divide by the spring constant. And now here's how you earn both of your B points at once. Delta x squared goes on my y-axis. D goes on my x-axis. So then this entire expression is equal to my slope. I do not have to say how to solve for this. I can just do that. Now, if you graphed in any other valid method, please don't ask me if your method works. If it's linear and it's some equivalent to this, it's fine. There's a million ways to manipulate this one and get a valid linear relationship as long as you are consistent with your slope. So B1 is for graphing something that's actually linear, and B2 is the slope analysis. So you have to say like the slope relation. So this is straightforward enough. It's energy and work, but there's a lot of letters and stuff in this, but nothing terrible. And then we have like a sibling of this, where now it's a spring constant that we wish to calculate pushing a block up a ramp. So we we compress the spring different distances, and we see how high up it goes. Well, this is just standard energy conservation. There's no work that we're really considering here. So max height and spring constant. So this is, of course, just saying 1/2 ks squared is equal to mgh. It's probably easiest to solve for h. So h would be equal to k divided by 2mg times s squared. So that gets us one possibility. I actually don't think I want to do that one, though. I think I'd rather put s squared on the y. I think that's what I did. So we'll actually show both. I think we'll show both. So one thing you could do is you could graph h on the y. You could graph s squared on the x. So your slope would be this object. I think what I personally graphed on the next page was just the reciprocal of this, where I graphed s squared equals 2mg divided by k times h. Anything equivalent to either of these also works. Now, I totally forgot what I did, so we're going to find out together. Insert, I did mining off camera joke here to show my graph. I did graph h on the y, so I actually did do this one. So regardless of what you picked, you better be getting at least 3 points on your graph. So if you picked a linear relationship, you got C1. So any variant of h and s squared with whatever numbers of your choice there. Axes, scale, and units. So just doing your units properly, scaling properly, linear scale, all that fun stuff. Then you got to plot the points in a reasonable spot. So here, since I actually wanted to graph s squared, I squared the s's somewhere. So I actually squared the s's in there. That's my squared values of s, but you can just trust I did it. And then making a reasonable best fit line is C4. So now I just hit linear regression button on Desmos with that, and I got this equation. And from our analysis earlier, we said from this form, the slope is k divided by 2mg. So if I wanted to solve for the spring constant, k would just be 2mg times the slope, which is 2 times the mass is 2 kilograms, g is 10, fight me, and the slope was 31.95. I say fight me because some of you are going to argue and say, I only use 9.8. That's fine. If you use 9.8, you're going to get a different answer, and I promise you the solution guides do both ways. So do not be concerned if you get a different value than me. So here we get, when I did this, I got approximately 1,280 newtons per meter. So I imagine things in the 1,200 range are about what we're expecting. So to get D1, you have to correctly relate K to the slope or y-intercept. In this case, it's the slope. And to get D2, your answer has to be correct. Now, what's the range? Who knows? I have no idea what the correct range will be. Probably pretty wide because you could use 10 for G or 9.8. But yeah, I thought the lab question was pretty easy, all things considered. Maybe it's definitely harder than last year's, though. So far, question 1, 2, and 3 are harder than last year. It is just energy conservation, but there's a lot of symbols to work out. And last year, one of them was linear already. All right, now we have something, question 4, that looks really, really scary, except it is perhaps one of the easiest rotation questions I've ever seen. This is easier than the question AP Physics 1 got for rotation. So a unicycle is on a stand. The wheel does not touch the ground. We have rotational inertia given, and we attach this sort of crank that exerts a force F on the wheel, causing it to rotate. So you could apply the force with a short crank arm L1, or you could use a long crank arm L2. So we either have like a short crank arm or a long crank arm to apply the force at. So this should already, definitely this is like a torque problem, right? It's literally called a crank arm, and we have this idea of lever arm for torque. So this is totally a torque problem. So it asks, after we spin the wheel once using a constant force at a constant distance, how do the speeds of the wheels compare? So is it bigger for the small crank arm or is it bigger for the long crank arm? Well, this is my thinking. So this is definitely about torque. You could also do this with energy as well. Like if you ever have a different solution, it's probably acceptable if it's correct, right? It does not have to be my solution. So torque is equal to R times F. And in this case, it's the same force F from the crank arm that can be applied. It's just the length that's different. So we are actually given that this force is the same. So this means that as the length of the crank arm increases, the torque increases. Well, okay, that's the most immediate effect, is that torque increases. So now what? Well, we also know that alpha, that torque is equal to I alpha, which means that alpha is proportional to the torque. That's some interesting symbol thing here. Alpha and proportional to. I'm not good at differentiating these symbols. So this means as L increases, alpha increases. And if alpha is the rate of change of omega, this means so omega increases for larger L. So this was my first solution. I just used kinematics basically and said, well, if you have a longer crank arm, you're getting more torque for the same force. So your wheel will accelerate at a greater rate around that same distance. So you get a larger angular speed after one revolution with the big turn. Now, another solution you could have done is you could have said that work equals torque times theta, where the theta that each revolves through was the same. It's 2 pi for a revolution. And that's also equal to delta K. So you could have used work energy theorem in angular form. So if you actually did the physics 1 free response, it actually could have helped you with this. But this is a pretty easy question. Same theta, and we also said torque increases as L increases. So more delta K in case 2. So speed increases with kinetic energy. Because if you have more kinetic energy, you obviously have a greater speed. And it's all angular in this case. So that's what I said. The force is the same in both scenarios, but the torque is greater in scenario 2 since the lever arm is greater. This gives wheel 2 a larger angular acceleration and therefore a greater angular speed over a set distance. I feel like you don't have to overcomplicate this one. There's not a lot of fluff you need here. The larger speed is 2, so that gets you A1. And I can make it more clear what my selection was. It's this. A2 is probably saying that the torque is greater in scenario 2. And A3 is probably saying that angular acceleration / angular velocity should relate to net torque. If you did energy, this point is probably relating like work to kinetic energy or something. Now we'll get a very easy, cool 3 points in B. Find omega 1. So this is just putting this stuff to words. So the net torque on our system is just going to be the force F applied at a distance L1, perpendicular to the wheel. So then we can say that our angular acceleration is just the net torque divided by the moment of inertia. We're allowed to use all of those things. So it's FL1 divided by I of the wheel. And this will be important. We have our acceleration. So we can now just plug in. We are not given time. So that tells us kinematics is involved, and it's the squared velocity ones. So I'd use omega F squared equals omega 0 squared plus 2 alpha theta. This is quite the fraternity here. So omega final would be the square root of 0 squared plus 2 times FL1 over I wheel times, what is delta theta? Well, it says after one revolution. So theta is just 2 pi because that's one revolution. And now we can just do that. So I'm not going to simplify out of that square root. I could have just left it as this and it's fine, but this would just be square root. So this is 4 pi FL1 divided by I wheel, all under a square root. And you can actually see that we'll get the same answer if we do energy. And energy is quick enough that we can do that. So if you did the forces approach, you get a point probably for like something with torque, multi-step with torque or kinematics, that's B1. Acceleration is probably B2, and then plugging in for the final answer with kinematics is B3. Now, if you did energy, you could just say work equals torque times theta, and the torque would be FL, and the theta would be 2 pi. But then you also know that that's equal to delta K. So I'd have 2 pi FL1 equals change in kinetic, 1/2 I omega squared minus 0. So notice I do get the exact same thing. Omega is just the square root of 2 pi FL1 divided by I wheel. As expected. You'd get B1 for work or torque. You'd get B2 for the actual like delta K term for figuring out the torque and the theta, and you get B3 for the final answer. All right, and then lastly, instead of a consistency, we're saying what if instead of just spinning the unicycle, we do the same force, but it causes the unicycle to roll without slipping. So any of these roll without slipping at constant force problems, it's about this sort of energy split. So if we allow the wheel to roll without slipping, not only is it spinning, but it's also translating. And if it spins and translates, well, that means you got to give its kinetic energy to multiple sources. So here's the quickest justification. So this would be scenario 1, where I have two kinds of kinetic energy. I have kinetic energy translational and kinetic energy rotational. And then in scenario 2, I also will do this. So in scenario 1, all of my kinetic was given to rotational because the wheel is not moving. So the input energy, which is the work, is the same. But in scenario 2, there's some translational KE as well. So what this means is in scenario 2, I still have to get sort of this same sum, but in scenario 2, some of my work was done to translate the wheel. So maybe I have something like this, where a lot of my energy went to the translational and only a little bit went to the rotational. So that's my quickest justification as to why the speed is now less, which gets you C1. And then C2 is a valid justification. I just said this, which is what I just said, but like in a ton of more words. The work done is the same because the force and distance are the same. Kinetic energy change is the same. And then the wheel must also have translational KE. So you have to split the same energy between two sources now. So you're not getting as much rotational KE, so not as much speed. Now, there's also a way you could have done this in terms of like friction force, where now you have to say there's a friction force between the wheel and the ground. And that friction force is going to oppose the rotation. It's going to be in that opposite direction. So the net torque decreases, so that net acceleration decreases angularly. So this is not pedal, I mean like crank arm. I think I misread this, but so the net torque on the wheel decreases, so the net angular acceleration decreases, so the angular speed decreases because there's now force kind of going the other way. So this is like a net force approach as well. So that gets you also C2 for saying something about net torque decreasing. Wow. Yeah, they definitely ramped it up this year. This is not a hard problem, and the lab question was manageable, but man, those first two were something else. Yeah. And from the sounds of it, the other forms probably weren't easy either. So this definitely seemed to be a harder year. It seemed that after 1 year of the new style of test, they ramped it up difficulty-wise to try to separate Physics C from Physics 1 and give you some harder scenarios. Only one of them required calculus, though. But man, the calculus required in the first one was tough. Okay. Let me know about anything. Hopefully they release the other forms, too. That would be nice. If you're curious about grading, let me know. I tend to be pretty good at figuring out points. So I'll help you with anything you want. Again, no idea what the cut score will be, but it really doesn't matter at this point. We'll find out in July.